In this chapter, we study the port capacity and expansion timing problem. The practical goal is to decide when to expand and what type of expansion to choose so the port can meet demand without falling into chronic congestion. We use the port of meridian as our setting and treat capacity as more than a static number. Capacity depends on infrastructure but also on operations and technology, so timing decisions must reflect both financial and operational dynamics. This slide establishes the pressure point. Port of Meridian is already handling 2.8 million 20-foot equivalent units per year, close to a theoretical capacity of 3.2 million. The most visible symptom is dwell time. It rises from 2.1 days to 4.3 days over 18 months, and this indicates that the terminal is operating near a tipping point where small demand spikes can create outsized congestion. Here we list the decision alternatives and their costs. A major berth expansion costs $450 million. A phased yard automation program costs $280 million spread over 3 years. And a comprehensive redevelopment program costs $750 million over 5 years. These options differ not only in cost but in implementation timing, operational risk, and how much capacity they add. That is why the timing decision is inseparable from the option selection. Timing matters because uncertainty is structural, not noise. Trade patterns shift, competitors expand, and regulation changes. If you expand too early, you lock capital into underutilized assets. If you expand too late, you incur congestion losses and potentially lose customers due to poor reliability. Also, port congestion does not stay local. It can cascade through carrier schedules, inland transport, and inventory systems. That network effect makes delay costs much larger than they first appear. This slide previews the tiered toolkit. We begin with a Markov decision process to model sequential decisions under uncertainty. Then we move to a fast heuristic, a global metaheuristic, and an artificial intelligence forecasting and planning approach. We then expand to system simulation through a digital twin, incorporate human judgment through a Centaur model, add ethical and value alignment constraints, and finally consider proactive market shaping as a way to reduce the need for physical expansion. Tier 1 frames the expansion decision as sequential planning. The state summarizes the capacity situation and the operational condition of the port. The action is the expansion choice, including the option to do nothing. This tier is valuable because it forces clarity. You must specify what the decision maker observes, what choices are allowed, how the system evolves, and how value is computed over time. This equation slide defines the state space. Each capacity state captures the current capacity level, the utilization level, and the age of infrastructure since the last major upgrade. Operationally, utilization is the key stress signal. When demand approaches capacity, congestion penalties accelerate. Infrastructure age also matters because older systems can limit throughput even if nominal capacity looks sufficient. This slide defines the action space. The decision maker can choose no expansion, a minor upgrade, a major berth expansion, or a comprehensive redevelopment. Each action has a different capacity gain and investment cost. These discrete choices are realistic for port governance, where you typically pick among a small number of capital programs rather than continuously adjusting capacity. This slide summarizes demand growth scenarios through transition probabilities. The system can transition under conservative growth, baseline growth, or aggressive growth. In an expansion context, these probabilities represent uncertainty in demand evolution. They also capture the idea that you are planning against scenarios, not a single deterministic forecast. This slide presents the reward structure. The port earns revenue on the throughput it can actually handle, which is demand limited by capacity. Against that, we subtract investment costs, congestion penalties tied to utilization, and maintenance costs. This is the core economic logic. Capacity that cannot be used does not earn revenue, while congestion can create large hidden costs that grow rapidly once utilization passes a critical threshold. This slide expresses the Bellman optimality principle. The best long-run value from a state is the best immediate reward plus the discounted expected value of the next state. The discount factor is 0.92, corresponding to an annual discount rate of 8%. This creates a disciplined way to compare near-term costs against long-term benefits. This diagram visualizes the Markov decision process transitions. It helps you interpret the model as a policy problem rather than a one-time investment decision. The diagram also emphasizes that expansion choices change the future state space. After an upgrade, utilization drops and the congestion penalty weakens, but maintenance and capital recovery considerations rise. This concrete example uses a three-state illustration. Starting at 3.2 million capacity and 2.8 million demand, utilization is about 0.875. The congestion penalty example produces about $1,162 per day, highlighting how costly high utilization can become. The reported policy insight is that a minor expansion is not worth the upfront cost immediately, and that delaying until utilization reaches about 92% maximizes expected net present value. Tier 2 introduces variable neighborhood descent. The idea is to define several neighborhood moves, such as shifting timing, changing capacity level, switching technology, or changing whether the plan is phased. Instead of being trapped by one local improvement rule, the method cycles neighborhoods. When one neighborhood can no longer improve the solution, the algorithm switches to a different neighborhood to continue improving. This figure illustrates the exploration pattern of variable neighborhood descent. It shows the concept of structured changes to the solution and a controlled way to escape local optima. Operationally, it is a practical planning method. Because each neighborhood corresponds to a change a port authority can actually consider and communicate, such as postponing a start date or adopting automation. This first code section defines how an expansion plan is represented in a way the heuristic can manipulate. A practical encoding includes items like the expansion start year, the capacity increase level, the technology choice, and whether the investment is phased. It also defines the neighborhood types. In this chapter, the neighborhoods correspond to changes a port authority can actually approve, such as shifting timing by 1 year, changing the capacity target, switching technology between semi-automation and full automation, or turning phasing on and off. This second code section typically implements the evaluation logic. For each candidate plan, the algorithm computes a value measure such as net present value over the planning horizon, while adding penalties for congestion and for operational bottlenecks. It also performs feasibility checks against constraints like investment caps and practical implementation timing. The key is that every neighborhood move must remain implementable, not just numerically attractive. This third code section shows the neighborhood cycling itself. The algorithm searches within one neighborhood until it cannot find improvement, then switches to the next neighborhood. Operationally, this is how variable neighborhood descent avoids getting stuck. A plan might be locally optimal with respect to timing changes, but still improvable if you allow a technology switch or a phased financing structure. This slide gives a full example run for Port of Meridian. The starting configuration is an expansion year of 2026, with a 40% capacity increase, which is about plus 1.28 million 20-foot equivalent units, using semi-automation, not phased, with an initial cost of $467 million. Variable neighborhood descent then improves the plan through structured moves. Delaying to 2027 reduces net present value cost by about $23 million. Switching to an 85% capacity increase raises total cost to about $694 million, but increases long-run value. Switching to full automation adds about $89 million, but reduces operating costs by about $31 million annually. Turning on 3-year phasing reduces peak financing by about $156 million. The final optimized plan starts in 2027, uses an 85% capacity increase phased over 3 years, and uses full automation. Reported total cost is $731 million versus the initial $467 million. But the net present value improves by about $178 million over a 15-year horizon. Tier 3 uses the gray wolf optimizer, a population-based meta-heuristic. Candidate expansion strategies are treated as wolves, and the best 3 solutions guide the rest of the population. This approach is effective when the decision space is high-dimensional and nonlinear, which is typical when timing, capacity size, technology choice, and phasing interact. This figure illustrates the pack hierarchy and the evolution of solutions over iterations. The alpha solution acts as the main guide, while the beta and delta solutions provide additional directional signals. Operationally, the value is that the method searches broadly early on and then concentrates around strong candidate strategies as evidence accumulates. This first code section defines how a candidate expansion strategy is encoded as a vector. A typical encoding includes phase timing, capacity increments by phase, and automation level by phase. It also defines the objective metrics used during evaluation, such as net present value, peak utilization or congestion penalties, and total investment subject to a budget cap. This second code section typically shows the leader update and the position update rules. The alpha solution is the current best strategy, and the beta and delta solutions provide additional guidance. In practice, this creates a controlled search. You move many candidates toward the leaders, but not in a single line, which helps avoid premature convergence. This third section usually focuses on objective evaluation and constraint handling. Each candidate is scored on net present value and service outcomes under demand growth uncertainty. Constraint handling ensures feasibility. If a candidate violates the $800 million cap or produces unacceptable congestion, the algorithm applies penalties so infeasible plans are driven out. This final code part usually ties the loop together. Update the exploration coefficient over iterations, re-rank solutions, and stop after a fixed iteration budget, or when improvement stalls. Operationally, the iteration budget is what makes meta-heuristics usable. You can decide, for example, that 180 iterations is an acceptable compute budget for a planning cycle. This example reports a 15-year planning horizon and demand growth from 4 to 12% per year under an $800 million budget cap. After 180 iterations, the reported phased plan invests $784 million and achieves a net present value of $847 million. It also manages peak utilization at 89%, and it improves net present value by 35% compared with a single large expansion strategy. Tier 4 uses a transformer architecture to learn patterns in sequential operational and market data. The attention mechanism helps the model focus on the most relevant historical periods and signals. In practice, this tier supports planning by producing probability distributions over expansion choices and by identifying timing windows that minimize congestion risk while respecting investment constraints. This figure shows the transformer architecture used for capacity planning. You can read it as an encoder that ingests historical signals and a head that outputs decision recommendations. The key idea is that long-range dependencies matter in port planning. The model can connect distant patterns in demand and operations to the current expansion decision. This first code segment typically defines the input representation. The model ingests sequences such as monthly throughput, berth utilization, gate efficiency, and external indicators over multiple years. It also defines embeddings and positional encoding, so the model can learn temporal patterns such as seasonality, long-run growth, and congestion cycles. This second code segment usually shows the attention blocks. Multi-head attention lets the model focus on different signals at once, such as how gate efficiency trends interact with berth utilization spikes. In capacity planning terms, this is how the model learns that bottlenecks can shift, and that the right expansion is often a coordinated package, not a single asset addition. This third code segment typically defines the output heads. One head predicts probabilities over expansion choices, such as no expansion, minor expansion, major expansion, or comprehensive redevelopment. Another head can predict technology choices such as semi-automation versus full automation, which is critical because dynamic capacity gains can change the optimal timing. This fourth code segment usually covers training. It defines the loss functions for classification outputs and any regression outputs, such as expected return on investment timing. It also defines how the model is validated across multiple ports, so it generalizes rather than overfitting one terminal's history. This final code segment typically shows inference and decision reporting. It converts raw model outputs into actionable recommendations, such as a recommended Phase 1 start quarter with a confidence score. In operations, this is where you also add safeguards. If the model suggests an aggressive plan, the system should still check budget and feasibility before presenting it as a recommendation. This example reports training on 15 years of monthly data from 12 major container ports. The model outputs decision probabilities, such as a 61% probability for a major expansion and a 61% probability for full automation. It also predicts a Phase 1 start in quarter 3 of 2025 with 89% confidence, with capacity online by quarter 4 of 2026. A key implication is that waiting until 2027 could create $340 million in congestion losses. Tier 5 introduces a digital twin that links berth operations, yard operations, gate processing, intermodal integration, and the broader supply chain network. The value is that capacity is not just berth count. A berth expansion can shift the bottleneck to the gate or the yard. Simulation makes these interactions visible before capital is committed. This architecture figure shows the main digital twin subsystems and how data flows between them. In a capacity planning context, the twin supports what-if analysis and stress tests. It can estimate utilization, dwell time, queue time, and system efficiency under different expansion and automation programs. This slide compares 3 alternatives against the baseline. The baseline shows peak utilization at 94%, dwell time around 4.1 days, and gate queues around 2.3 hours. A berth addition reduces utilization and dwell time but leaves the gate as a bottleneck. Automation improves gate processing and reduces dwell time, but does not add berth capacity. The integrated approach achieves the strongest system-wide outcome by addressing both capacity and process efficiency. This example quantifies the digital twin at Port of Meridian using 847 Internet of Things sensors and 12 operational systems. The integrated approach invests $720 million across 4 phases and reports system efficiency at 92.4%, with full elimination of peak period delays and a net present value of $634 million. The point is synergy. Combined investments can outperform linear, isolated upgrades. Tier 7 emphasizes that real port expansion decisions require qualitative judgment, politics, labor relations, community impact, and regulatory feasibility. The Centaur model combines human context setting with AI scenario generation and ranking. The result is a decision process where AI explores a larger space than humans can, while humans ensure that the final plan is implementable and socially acceptable. This figure shows the workflow of a human and AI partnership. Humans define constraints and priorities, AI generates scenarios, humans evaluate feasibility, and AI refines recommendations with feedback. Explainability is essential here because decision makers must understand why a timing recommendation is preferred and how sensitive it is to uncertainty. This example reports an AI system generating 15,000 scenarios and presenting the top 50 for expert review. Human constraints include environmental footprint limits, an 18-month labor notice requirement, and a financing window from 2027 to 2029. The final recommendation starts in 2027 with an automation-first approach and an 18-month labor transition beginning in quarter 1 of 2026. It reports a net present value of $623 million and stakeholder acceptance probability of 94%. Tier 8 adds explicit ethical and value alignment requirements. Instead of maximizing net present value alone, the optimization also protects environmental justice, labor equity, and fair distribution of benefits. In practice, this reduces the risk of backlash and delays, which can be decisive in large infrastructure projects. This framework figure shows how multiple stakeholder values are represented and incorporated into a decision process with transparency and accountability. The main operational idea is that the best plan is not just the one with the highest financial return. It is the plan that is feasible, legitimate, and sustainable over time. This slide provides examples of ethical constraints expressed in a form the optimizer can use. Environmental justice limits disproportionate impact on vulnerable communities. Labor equity limits displacement relative to job creation and retraining capacity. Fair benefit distribution ensures local communities receive a meaningful share of gains. These constraints define non-negotiable guardrails for technology and expansion decisions. This example compares a purely economic solution with a value-aligned solution. The economic plan reports net present value of 634 million, but higher environmental impact and higher job displacement with low community benefit share. The value-aligned plan reports net present value of 578 million, but it cuts environmental impact and job displacement substantially and increases community benefit share to 31%, with stakeholder satisfaction rising to 87%. Tier 10 shifts the mindset from building capacity to shaping demand. Ports can influence scheduling and cargo flows using incentives, pricing, and coordination with shippers and carriers. The objective is utilization smoothing, which reduces peak congestion and improves reliability without immediately expanding physical infrastructure. This figure frames the port as a market orchestrator. It uses pricing and service design to encourage behaviors that reduce bottlenecks, such as off-peak arrivals or more predictable scheduling. In capacity planning, this is powerful because it can delay major capex while maintaining service quality. This example describes time-based pricing with peak surcharges and off-peak incentives, plus a bonus for schedule reliability within a 4-hour window. It reports shifting 23% of peak volume to off-peak, raising revenue by 18%, and smoothing utilization so peak drops to 87%, while off-peak rises to 81%. The headline outcome is a throughput increase of 1.1 million TEU per year without immediate capacity expansion. These practice questions are designed for implementation readiness. You practice building a Markov decision process and solving a small value iteration example, and you practice coding variable neighborhood descent and gray wolf optimizer iterations. You also practice specifying a transformer model, designing a digital twin architecture, defining Centaur collaboration protocols, incorporating ethical constraints, and designing pricing incentives to achieve target utilization patterns. To close, capacity expansion is a sequential decision under uncertainty. Different tiers provide different strengths, from rigorous planning foundations to scalable search and learning-based forecasting. The broader lesson is that good capacity planning is multidimensional. You need operational realism, system-wide simulation, stakeholder feasibility, ethical guardrails, and sometimes market design to reduce the need for physical expansion.